Meta's breakthrough in brain-computer interfaces, decoding thoughts into text. On February 6 to 7, 2025, Meta, the tech giant formerly known as Facebook, made headlines with the release of two groundbreaking research papers from its fundamental artificial intelligence research FAIRE Lab. These papers detail significant advancements in brain-computer interface (BCI) technology, specifically focusing on the ability to decode brain activity into text with an impressive accuracy of up to 80%. This technology, which employs non-invasive methods, has profound implications for communication, particularly for individuals who have lost their ability to speak due to neurological conditions. Overview of the research. Study 1, Brain 2 QWERTY. The first paper introduces a model named Brain 2 QWERTY designed to convert brain activity into typed sentences using non-invasive techniques such as magnetoencephalography (MEG) and electroencephalography (EEG). The research was conducted with a cohort of 35 healthy volunteers who were tasked with typing brief, memorized sentences. The model achieved an average character error rate (CER) of 32% when using MEG, significantly outperforming EEG, which recorded a CER of 67%. For the top-performing participants, the model's CER was as low as 19%, demonstrating that Brain 2 QWERTY can effectively reconstruct sentences based on brain signals. This advancement narrows the gap between invasive neuroprosthetic devices, often requiring surgical procedures, and non-invasive methods, paving the way for safe and practical BCIs for patients who have lost communication abilities. The potential applications of this research could be revolutionary, offering new hope for individuals suffering from conditions such as ALS, stroke, or traumatic brain injuries. Study 2, Neural Mechanisms of Language Production. The second study delves deeper into understanding how the brain processes language. By analyzing brain activity while participants typed, researchers identified a structured sequence of neural activity that transforms thoughts into words. This research revealed that the brain employs a dynamic neural code which allows for the simultaneous representation of multiple successive thoughts. It highlights how abstract concepts are gradually transformed into specific words and motor actions, providing insights into the neural architecture of language production. Key findings and implications. 1. Decoding mechanisms. The ability to decode thoughts into text offers a non-invasive alternative to traditional methods which often require surgical intervention. This could lead to the development of user-friendly BCI technologies that assist those with speech impairments. 2. Cognitive neuroscience contributions. The findings contribute significantly to our understanding of how language is generated in the brain. By elucidating the neural dynamics involved in language production, this research can enhance the development of AI models aimed at improving speech assistance technologies. 3. Challenges ahead. Despite these promising results, several challenges remain. The performance of the decoding model is not perfect and requires further refinement to enhance accuracy. Additionally, practical concerns such as the need for participants to remain still in a magnetically shielded environment pose limitations for broader applications. For future research directions, ongoing studies will need to validate these findings with patients who have lost their ability to communicate. Research teams aim to explore how these technologies can be made more accessible and effective in clinical settings. Broader impact. Meta's commitment to open science is evidenced by their collaboration with leading neuroscience institutions and a substantial $2.2 million donation to the Rothschild Foundation Hospital to support further research in this area. This collaborative approach aims to bridge the gap between technological advancement and practical application in healthcare. The implications of this research extend beyond medical applications. They also touch upon philosophical and ethical considerations regarding the nature of thought and communication. As technology progresses, the potential to read thoughts raises questions about privacy, consent, and the human experience of communication. Timeline of Meta's journey. 2017, Meta initiated its Typing by Brain project, laying the groundwork for future advancements in non-invasive communication technologies. February 6 to 7, 2025, the two pivotal papers were published detailing breakthroughs in decoding language from brain signals and understanding the neural dynamics of language production. February 13, 2025, major news outlets including Tweaktown reported on these advancements, emphasizing both the technical achievements and their potential applications for restoring communication among individuals affected by neurological conditions. Conclusion: Meta's recent research marks a significant leap towards integrating AI with neuroscience. The ability to decode thoughts into text through non-invasive methods stands to revolutionize the way we understand communication and assist those who have lost their ability to speak. As the field of brain-computer interfaces evolves, continued collaboration and exploration of these findings will be essential to overcoming existing challenges and unlocking the full potential of this technology. The journey initiated by Meta could lead to new horizons in human communication, cognition, and the very understanding of what it means to think and express oneself. Meta's recent research breakthroughs in brain-computer interface (BCI) technology reveal several counterintuitive insights regarding the decoding of thoughts into text. Here are the notable points. 1. Non-invasive versus invasive methods. While invasive neuroprosthetics have been the norm for restoring communication in patients with speech loss, Meta's research emphasizes non-invasive methods using magnetoencephalography (MEG) and electroencephalography (EG). This contrasts with traditional beliefs that effective brain signal decoding necessitates surgical intervention. The findings challenge the assumption that only invasive techniques can yield high accuracy in decoding brain signals. 2. Character error rate (CR) insights. The papers report an average character error rate (CR) of 32% with MEG and 67% with EEG, which, while seemingly high, is considered a significant achievement in this field. The fact that some participants achieved a CER as low as 19% suggests that with more training and refinement, the technology could become even more accurate. This counters the expectation that achieving high fidelity in thought decoding is insurmountable. 3. Dynamic neural code. The research uncovers that the brain employs a dynamic neural code which allows it to maintain coherence across multiple thoughts simultaneously. This insight contradicts the conventional view that thoughts are processed sequentially, one at a time. Instead, the brain appears to handle layers of information at once, enabling a more complex understanding of language production. For practical challenges and future directions, the studies acknowledge practical limitations such as the requirement for participants to remain still in a magnetically shielded room during MEG recordings. This highlights a paradox. While the technology offers a potential breakthrough for communication restoration, its current application is severely limited by the necessity for controlled environments, raising questions about its usability in everyday settings. 5. Implications for communication restoration. The potential applications for patients who have lost the ability to communicate are profound. Yet the research emphasizes that the technology is still in the experimental phase. The notion that it could soon be widely applicable is countered by the acknowledgement of ongoing challenges that must be addressed before it can become a practical solution. 6. Collaborative efforts in neuroscience. Meta's commitment to collaboration with neuroscience institutions illustrates an unexpected approach to advancing BCI technology. This cooperative model contrasts with typical tech industry practices where proprietary research predominates, suggesting that shared knowledge could accelerate breakthroughs in understanding brain function. 7. Cognitive factors in decoding. The research indicates that typographical errors during typing tasks are influenced not only by motor processes but also by higher-level cognitive functions. This duality suggests that the process of translating thoughts into text is more intricate than previously understood, challenging the simplistic view that thought-to-text conversion is merely mechanical. 8. Potential for AI integration. The studies propose that understanding the neural dynamics of language production could significantly enhance AI models for speech assistance. This notion challenges the idea that AI development must solely rely on traditional data-driven approaches, suggesting that insights from neuroscience could lead to more sophisticated AI applications. In summary, Meta's research reflects a paradigm shift in understanding how thoughts can be decoded into text, emphasizing non-invasive techniques, uncovering complex neural dynamics, and recognizing the practical hurdles that remain. These findings challenge established notions about language processing and the feasibility of real-time thought decoding, paving the way for future advancements in both neuroscience and AI. Meta's recent publications on brain-computer interface (BCI) technology reflect a significant leap forward in our understanding of how to decode thoughts into text. Achieving up to 80% accuracy in real time with non-invasive methods. While the core findings are noteworthy, several subtler aspects of the research may be overlooked but are crucial for understanding its full implications and future directions. 1. Dynamic neural code and its implications. One of the most significant aspects of this research is the concept of a dynamic neural code that the brain uses to process language. This notion, while touched upon in summaries, holds deep significance for both neuroscience and artificial intelligence. The ability of the brain to maintain coherence across successive thoughts and simultaneously represent multiple layers of language is a profound insight into human cognition. Significance. Understanding this dynamic neural coding could lead to enhanced AI models that better mimic human language processing. Current AI systems often struggle with maintaining context over longer passages of text or speech. By leveraging insights from how the brain organizes and transitions thoughts, future AI could become more adept at generating coherent and contextually rich responses, making interactions more natural and effective. 2. Non-invasive versus invasive techniques. The research emphasizes the non-invasive nature of the methods employed, MEG and EEG, compared to existing invasive neuroprosthetics. This is a critical point, often overshadowed by the immediate findings of the model's accuracy. Significance. The potential for non-invasive techniques to restore communication for individuals with speech impairments is immense. Unlike invasive methods that require surgical interventions and carry inherent risks, non-invasive BCIs could be more widely adopted, reducing the barriers to accessibility. This could revolutionize rehabilitation for stroke victims, ALS patients, and others who have lost their ability to communicate, ultimately improving their quality of life. 3. Character error rate (CER) and its implications. While the papers report a character error rate (CER) of up to 32% with MEG and 67% with EEG, the fact that some participants achieved a CER as low as 19% is particularly noteworthy. Significance. This variance suggests that individual differences in brain signal patterns and typing skills play a substantial role in decoding accuracy. Future research could focus on identifying these individual differences and tailoring BCI systems to optimize performance for specific users. Understanding the factors that contribute to these differences could also inform training protocols for both users and the AI models themselves, enhancing overall effectiveness. 4. Collaborative efforts and open science commitment. Meta's commitment to collaboration with leading neuroscience institutions and its $2.2 million donation to support further studies illustrate a significant investment in the scientific community. Significance. Such partnerships can accelerate research by pooling resources and expertise, leading to faster advancements. Moreover, this commitment to open science fosters transparency and encourages other researchers to build upon Meta's work, potentially leading to new innovations and applications in the field. This collaborative approach could establish standards and best practices that benefit the entire field of neuroscience and AI. 5. Challenges and future directions. The research acknowledges several challenges, including the need for improved accuracy and practical applications. While these challenges are mentioned, the implications of addressing them are profound. Significance. Overcoming these hurdles is essential for translating lab-based successes into real-world applications. Future research must not only focus on improving decoding accuracy but also consider user experience, including how these systems can be seamlessly integrated into daily life. This could involve developing portable devices that do not require a magnetically shielded room or training programs that help users adapt to new communication methods. 6. Neural dynamics of language production. The study's exploration into how thoughts transform into words, particularly through the lens of neural dynamics, is a critical area of investigation that extends beyond the immediate applications of BCI. Significance: this understanding can inform various fields including linguistics, cognitive psychology, and even education. Insights into language processing could lead to better educational tools and strategies that align with natural cognitive processes. Moreover, understanding the neural mechanisms that underpin language could enhance therapies for language disorders, providing targeted interventions that align with how the brain naturally organizes and processes language. 7. Broader implications for AI development. Finally, the implications of these findings extend into the realm of AI development beyond BCIs. The insights gained from this research can inform advancements in natural language processing (NLP) and machine learning models. Significance: as AI continues to evolve, incorporating principles derived from human cognition could lead to systems that not only perform tasks but understand context and intention more deeply. This could pave the way for more intuitive AI applications in various domains, from customer service to personal assistance, enhancing interactions between humans and machines. In conclusion, while Meta's breakthrough in decoding thoughts into text has garnered significant attention, the overlooked aspects of their research, such as the dynamic neural code, the non-invasive nature of the technique's individual differences in performance, and the collaborative commitment to open science, are equally important. These elements not only enhance our understanding of human cognition but also lay the groundwork for future innovations in communication technologies and AI, emphasizing the need for continued exploration and investment in this promising field. 1. Non-invasive brain-computer interfaces (BCIs) and their implications. Meta's research emphasizes the development of non-invasive techniques, specifically through the introduction of the Brain 2-QWERTY model, which decodes brain signals into text with up to 80% accuracy. This advancement represents a significant shift from existing invasive neuroprosthetic methods that involve surgical intervention, bringing hope for communication restoration to individuals with speech impairments due to neurological conditions. The non-invasive nature of these techniques not only reduces risks associated with surgery but also opens the door for broader applications in clinical settings, making BCIs more accessible to patients who traditionally have limited options. 2. Dynamic neural code and language production. The second paper sheds light on the intricate neural mechanisms that govern language production. By revealing that the brain employs a dynamic neural code, the research illustrates how thoughts evolve into coherent sequences of words and actions, maintaining multiple layers of information simultaneously. This understanding can significantly enhance the development of AI models for speech assistance technologies, as it provides insights into the cognitive processes involved in language generation. By comprehending how the brain organizes and processes language, researchers can improve AI's ability to assist humans effectively. 3. Challenges and limitations. Despite the impressive accuracy rates achieved with the Brain 2-QWERTY model, challenges remain in translating these findings into practical real-world applications. The current requirement for participants to be in a magnetically shielded room and remain still poses practical hurdles for deployment in everyday scenarios. Additionally, the error rates, particularly with EEG recordings, highlight the need for further refinement of the decoding processes to ensure reliable communication. Addressing these challenges is crucial for the successful integration of BCI technologies into clinical practice and everyday life. 4. Collaborative research and open science commitment. Meta's commitment to collaboration with neuroscience institutions and open science is a notable aspect of this research. The partnership with leading centers underscores the importance of interdisciplinary approaches in tackling complex challenges in understanding brain function and language processing. Furthermore, Meta's financial support for ongoing research initiatives illustrates the company's dedication to advancing scientific knowledge and fostering innovation. This collaborative spirit is essential for driving future breakthroughs in brain-computer interfaces and enhancing their practical applications in restoring communication for those affected by neurological disorders. 1. The BrainGate Project 2000s present. The BrainGate Project is a pioneering research initiative that focuses on developing brain-computer interfaces (BCIs) for individuals with severe motor disabilities. Through invasive techniques, the project has aimed to decode neural signals from the brain to control external devices. Notably, in 2004, a paralyzed individual was able to control a computer cursor using thoughts alone, demonstrating significant potential for restoring communication and mobility. While the technology relies on implanted electrodes, it has paved the way for non-invasive alternatives such as those being explored by Meta. 2. Neuralink's development 2016 present, founded by Elon Musk. Neuralink is a neurotechnology company that aims to create implantable brain-machine interfaces (BMIs). In 2020, Neuralink showcased a prototype where a pig had a device implanted that recorded brain activity, illustrating the potential for real-time decoding of neural signals. While Neuralink primarily focuses on invasive techniques, its advancements have stimulated discussions on non-invasive options similar to Meta's recent breakthroughs. The goal is to enable communication for individuals with neurological impairments similar to the applications of Meta's Brain 2 QWERTY model. 3. The WADA test in language processing 1960s. The WADA test, developed by Dr. John Wada in the 1960s, is a procedure that involves the injection of a barbiturate into one hemisphere of the brain to assess language and memory functions. This test has been crucial in understanding the lateralization of language processing in the brain. Although it is an invasive method, it has led to significant insights into how the brain organizes language production and comprehension. The findings from the WADA test have informed modern neuroscience and AI research, including studies like those conducted by Meta, which aim to decode how thoughts are transformed into language. The recent breakthroughs by Meta in brain-computer interface (BCI) technology, particularly in decoding thoughts into text with an impressive 80% accuracy, represent a pivotal moment in both neuroscience and artificial intelligence. As we look to the future, several key predictions can be made regarding the implications, advancements, and potential challenges of this technology. 1. Enhanced communication for individuals with disabilities. One of the most immediate applications of Meta's research is the restoration of communication for individuals with speech impairments due to neurological conditions. As non-invasive BCIs become more refined, we can expect to see clinical trials expanding into wider patient populations. This could transform the lives of those with ALS, stroke, or traumatic brain injuries, enabling them to communicate through thought without the need for invasive procedures. Over the next decade, the integration of these technologies into rehabilitation programs could significantly improve the quality of life for millions. 2. Advancements in neurotechnology. The research indicates a pathway to improving the accuracy and usability of BCI technologies. Future iterations of models like Brain 2 QWERTY will likely incorporate more complex algorithms, enhanced signal processing techniques, and possibly even hybrid systems that combine non-invasive methods with advanced AI models. As these technologies evolve, we can anticipate a reduction in character error rates, making real-time communication more feasible. Additionally, the development of more portable and user-friendly devices could see this technology transition from clinical settings to everyday use. 3. Ethical and privacy considerations. As BCI technology advances, ethical concerns surrounding privacy and consent will become paramount. The ability to decode thoughts raises significant questions about mental privacy and the potential for misuse. In the future, robust ethical frameworks will need to be established to govern the use of such technologies. This includes considerations for informed consent, data security, and the potential for unauthorized access to thoughts. Ongoing public discourse and regulatory oversight will be crucial to navigate these challenges responsibly. 4. Integration with artificial intelligence. The findings from Meta's research not only advance our understanding of language production in the brain but also pave the way for improved AI systems. As AI learns from the dynamic neural codes identified in these studies, we can predict a future where AI systems can better interpret human intent and context. This could lead to more sophisticated natural language processing applications, enhancing everything from virtual assistants to automated customer service interactions. 5. Collaborative neuroscience and AI research. The publication of these studies demonstrates a commitment to open science and collaboration between AI researchers and neuroscientists. In the coming years, we can expect to see an increase in interdisciplinary research initiatives aimed at further unraveling the complexities of human cognition and language processing. This collaborative spirit could lead to breakthroughs not only in BCI technology but also in understanding cognitive disorders and developing targeted therapies. 6. Potential for broader applications. Beyond communication restoration, the implications of Meta's research extend into various fields. For instance, educators could leverage BCIs to tailor learning experiences to individual cognitive processes, enhancing educational outcomes. In mental health, BCIs could facilitate new forms of therapy, allowing practitioners to gain insights into patients' thought processes. Furthermore, industries such as gaming and entertainment could explore immersive experiences driven by thought, creating entirely new forms of interaction. 7. Challenges in real-world implementation. Despite the promising advancements, several challenges remain before BCIs can achieve widespread adoption. Technical limitations such as the requirement for stillness and the need for magnetically shielded environments must be addressed. Additionally, the technology's scalability and cost-effectiveness will be critical factors in determining its accessibility to a broader audience. Overcoming these hurdles will require significant investment in research and development. 8. Public perception and acceptance. The future success of BCI technologies will heavily depend on societal acceptance. Public perception of neurotechnology can fluctuate based on cultural attitudes toward technology and privacy. Education and transparency about the benefits, risks, and ethical considerations of BCIs will be essential in fostering trust and acceptance among potential users. Conclusion. Meta's advancements in decoding thoughts into text signal a transformative era for communication and human-computer interaction. As we look ahead, the integration of neuroscience and AI has the potential to revolutionize numerous aspects of society, from healthcare to education to entertainment. However, alongside these advancements, careful attention must be paid to ethical considerations, public perception, and the practical challenges of implementation. With thoughtful development and collaboration, the future of brain-computer interfaces holds the promise of profound change in the way we communicate and interact with technology.